Sí, sí, voy a presentarle, pero primero lo voy a poner a... ¿Te puedo hacer una pregunta por diapositiva?
Bueno, entonces acabamos a las 2. También es mañana a las 7 de la mañana, o sea que me da tiempo, yo creo. Pero, up to you.
Okay. Okay, thank you very much for being here for the new season of seminars. Today we have Carlos Hernández Monteagudo, and I don't have to introduce him too much. He's a former colleague. He's now working at the IEC.
Still a colleague of yours. Still an astrophysicist, therefore I'm a colleague. Acepta colleague, okay?
From the center.
Okay.
And today he's going to talk us about the tomographic clustering analysis of J-PLUS DR3 galaxy counts and redshifts.
Thank you. Listen up. So thank you for the introduction, thank you for the invitation. So this talk is a summary of the work that I've been doing. I started this project many years ago, but then I interrupted it, and I resumed. But finally, I think that I hope to have like a version of the paper to be shared with you by the end of next week, right? I'm polishing the bibliography, and I was hoping to have it before this talk, but usually unexpected things happen, come along, and this is life. This is a bit crazy because I'm trying. Initially, I was just trying to test cosmology and to test the clustering tools that we're developing for J-PLUS. We developed J-PLUS on J-PLUS. Of course, we cannot do much cosmology because J-PLUS is shallow. But yet, it's been an interesting experience to do because we have learned a lot about the tools, about the data, and we have some idea on what to expect for J-PLUS, right? So, Leo was asking me how many slides of these equations I had. I had a few, but just a few. Anyway, I try to keep it simple. Stop me any moment. And I try to make it accessible for those who are not specialists on cosmology, precisely because we cannot do much cosmology because of the data, right? So it's pretty much fighting against systematics and just computing the power spectrum, some statistics that we use in cosmology, and comparing theory with the data. And what we're pretty much doing is just simply measuring the bias, right? I don't know how many of you are familiar with the bias, but I try to explain this in the slides, right? I guess I don't need this slide yet. I put it there, right? So this is the DR3. So this is the area, effective area. After masking, actually, when I was doing the clustering studies, I found that there is some bit here close to the galactic galactic center that is very crowded, contaminated with the stars, and I had to remove it. And there's another region around here which is way too deep, which is the initial or early data rate for J-PLUS. I had to remove it as well because I was screwing up on the analysis, right? So in reality, I don't have 2800, I have 2700. So, or maybe I have no, I think I told like 800 is what it is, around 2800 what I have, right? Not much, right? The thing is, I was trying to do clustering. Initially, I was very motivated saying, hey, maybe we can measure peculiar velocities. Peculiar velocities are interesting for cosmologists because they are triggered by gravity. And we can test cosmology by looking at the peculiar velocities, by looking at how gravity evolves and how these velocities evolve with time. Is telling us how the universe is expanding at what rate, and that dark energy is influencing this expansion rate of the universe. So initially I was targeting the peculiar velocities with J-PLUS. In reality, as I will show next, we're not really sensitive to these velocities, but we're not too far away, which is something like okay, it's not a too bad result. For this reason, I was using these high odds. I guess that all of you are familiar with odds, otherwise Antonio has done a poor job here, and sort of they have done very well in defining. There's no equation defining what the odds is just a parameter telling you how packed, how collapsed is the PDF or the photosys, and just retaining out of the few million sources that we had in the initial sample for galaxies, like say half of them are galaxies. After imposing R below 21 and odds, by the way, I'm correcting for galactic extinction, as I was suggested last year. And imposing this thing, then I am left with around 300,000 galaxies, the entire 3,000 square meters. Okay? And you can see how, and then of course I have to identify galaxies, but that's not my job, right? So they are already well, that's not my job. I was initially using Cardenio's separator, but then these two papers came along. probability of margins using this the default machine learning algorithm that is selecting in a pool of other machine learning algorithms the most optimal one, which seems to be a CA boost. And then there is this paper by Andrés del Pino, right? Sorry?
It is Banjos, no Banjus.
Two ends,
Two N's and one O.
neural network.
Like in the plot. Yeah.
Like in the plot.
Yeah.
Okay, so it was me yesterday doing the speeding up with the top. Okay, good. At least I don't have to redo the plot. Changing the slides and changing the plots. Thank you. And then one is this one. The thing is that they are close, but they are not the same, right? You see how this is the DND set, the number of galaxies per unit square degree for different redshift bins. I'm using the maximum likelihood of that Antonio is producing. And you see that they tend to coincide only at very high odds, right? At lower odds, there is more discrepancy. And actually, I'm not going beyond 0.2, 0.25, because here I have to, this typically sources are too faint, and systematics are going to impact a lot in the spatial distribution. So clustering analysis are top beyond 0.25 or so, as I show next. Okay. So what I'm doing is I'm doing tomography, right? I'm doing redshift shells in steps of 0.02 from redshift 0.05 up to 0.025. And then for every redshift central redshift in this redshift range, I'm considering 3 different widths. Okay. And from this, I'm studying the clustering under each of these shells. So this is an example of things that I'm using. This is the DR, this is the footprint for J-PLUS DR3, and this is a typical density contrast. This is what we use in cosmology. This is just telling you how many galaxies you have in a given pixel. This is J is running over all galaxies belonging to a given pixel, over the angular average on the whole footprint. These brackets here with n is just denoting an ensemble average over the entire area. You have available -1. So if you have an average number, in this pixel you have exactly the average number of pixels of galaxies that you have in your pixels. This is unity -1, and then the density contrast is 0, right? You see that you have clusters or groups which have a lot of galaxies, but most of the space is actually blank or hollow, right? This is what you expect for a nearby universe. Okay. This W is simply a Gaussian weight because I'm doing tomography. I'm just applying a Gaussian weight to all galaxies. This is the redshift of the galaxy. This is the central redshift of the shell I'm considering, and this is the width I'm adopting. I'm doing tomography with different versions. So typically, the density contrast, for many galaxies, you go on 3, and when you have empty pixels like here, you have -1. This is 0, and you're just left with -1. Okay. So the statistical angular properties of this field can be predicted from at least for linear theory. In cosmology, you assume that this thing is small enough to produce predictions. Okay. But then you have systematics, right? This is using the database. I was just inferring as many systematics as I could. Many of them are correlated. Like I'm using 2 maps for the distinction. I'm using different depths, but they are very correlated. Whatever the exposed, the effect is very correlated, and so on. They're not independent. But I just want to use this as possible templates that are potentially biasing the observed number of galaxies that they observe in a given pixel. So the observed number of density, so the number of galaxies that observed in a given pixel is the cosmological one. But then I leave room for an additive. If I have a template in my footprint of all these systematics, and I do have those because this I can infer from the data, then I can assume that, okay, maybe what I'm observing is what is there in nature, in the universe, plus some contamination, which may be additive or maybe multiplicative. Okay, this is the deviation from the angular fluctuations. This is a constant, an angular average, and then you have the angular fluctuations. Angular fluctuations may be biasing, modulating the observed number of galaxies in a multiplicative or in an additive way. Okay. So last year I was presenting a paper. I shared a paper with the collaboration. I haven't submitted it yet because I want to submit it to this paper as well. One would provide a method to measure these betas and these alphas. Okay, and correct. Right. So this is before correction, like even shell at 0.15 and with 0.05, and this is after correction. So you see that we have many more galaxies along the galactic plane, and this is the difference, right? Pre minus post. So in reality, we were losing some galaxies because of high density of stars, and then we had like too many because this is way too big. There are some very big regions there. This I showed last year, I believe. And then I'm using 2 statistics, right? I'm using this thing, which is I already introduced, which is just simply the number of galaxies over the average -1. This is telling you the excess or the effect of galaxies over the average. This I call angular density fluctuations, because this is done under a given Gaussian shell, and you do it in a tomographic way, which is the standard 2D clustering. And then there's a new cosmological observable that I developed when I was here at TEFCA, and which is I'm testing here with the data, which is called angular redshift fluctuations, which is similar to the previous one, but here, instead of just simply counting number of galaxies, what I count is the redshift of a galaxy minus the average redshift of all galaxies under the same Gaussian shell. Okay, so you can see that by eye that they change a lot, right? Here, it's a very wide map, you are close to 0, and only a few pixels you are minus 3 sigma or plus 3 sigma. It's a Gaussian statistic per se, right? But yeah, our claim was that it contains a lot of cosmological information. It should be used and it should be added on top of the ADF, right? So this is what we're developing here. But before that, we need to correct for systematics, right? So this is the result of correcting for the betas and the alphas. In reality, I don't have the alphas, I have the epsilons, which is something that goes from 0 to 1, right? So 0 is no correction, no contamination. 1 is a contamination equal to the average number density of galaxies under a given shot. It's a big contamination. Redshift is increasing downwards, okay? Downwards. And here in the x-axis are the different systematics, right? So you can see that at low redshifts, little presence of systematics, maybe this way, right? But as you go to redshift 15, I start to have these are anti-correlated. The fact that these are positive, negative, negative, positive, negative, positive, they kind of tend to cancel out because these two templates, which is noise and effective time, are very anti-correlated, so yes, they may cancel out. But what you can see here is that beyond redshift 0.15, we have issues. And beyond 0.25, we have a lot of issues. There's a lot of contamination. So yeah, corrections around 0.50. You have a spurious number of galaxies that is 50% of your average, means that you have to worry about how accurate your subtraction your correction is. So I start not to believe things below 0.25%. So I stop here. I could have gone further, but I want to stop here. This is for the additive, this is for the additive contamination, and this is for the multiplicative. The multiplicative corrections are usually milder, lighter, not so serious, only up to 0.25 when they become again serious, right? So give you an example. So this is it, right? So I'm applying this correction. This is to tell you, to motivate that I'm going to stop at 0.25. And then some equations, sorry, right? So we have galaxies, we have density contrast, we have ADF or ARF on the sphere. So it's customary to develop this, to expand this on spherical harmonics. And then we look at these harmonic coefficients, which have some statistical properties. In cosmology, all this density, the density field comes from the inflation, it's a Gaussian random field that then evolves through gravity and so on. But at least on the large scale, it should be random, it should be Gaussian. And for random numbers, for random fields, you have that if you compute the standard, the ensemble average of these two coefficients, they are 0 unless you are coupling exactly the same multiple, right? The same L, the same M. And actually, this average is called the angular power spectrum, right? Which is related to the angular correlation function. This pretty much is the harmonic transform of the angular correlation function, but in reality, it's just the average of, after fixing M equal, I should have written here M and L, and not M prime and L prime, so I have to correct as well. But anyway, for you just average for a given L, you average over all possible M's, and then this is the amplitude, which is telling you how much angular anisotropy your map has on a given angular scale of L. L is typically inverse number of angle, right? L equals roughly pi over theta, and theta is the distance between two. It's a scale on the map, right? For a given angular distance, you have a wave number which is L, which is pi over theta. Okay. And then if you have two different fields, you see how I have a superscript here, I, right? You may compute how similar a map I is compared to different map J, right? So you may compute the cross angular power spectrum, which is you compute the harmonic coefficients for the different two maps, you multiply them, and then you end up with a cross angular power spectrum, which is C, J, where J is different from I, right? If you can do the auto power spectrum, what you're doing when I equals J, which is for a given map. But if you want to see how similar two different maps are, what you can do is that you compute the cross correlation, you compute the cross angular power spectrum, which is coupling the multiples from different maps. And this correlation coefficient is simply telling you how similar these two maps are. This is just the cross correlation coefficient over the sum over the autos, the square root of the product of the autos, right? If this is close to 1, is that the maps I and J are very similar. If this is close to 0, is that they are very dissimilar because the ALM coefficients are very different and the average to C, pretty much, right? So in order to test for systematic residuals, I'm computing this correlation coefficient, right? So you see, this is before correction, this is after correction. I think I've shown this plot before as well. Before corrections, I have this, so every row and every column here are different redshift shells. This is for narrow shells, middle width shells, and wide shells, right? This is the width. And what you can see is that very different, for instance, this redshift shell of 0.14 or so seems to be highly correlated with a shell which is very far away. This is not cosmological, right? This has to be. So this is before correction. After the correction, I was telling you, you see that off diagonal regions are whiter. So this means that we are correcting something here, but it's not perfect here. We have some residuals, right? But this is what we have. And and this is actually an actual limitation in all surveys, in all galaxy surveys. The CMB is usually cleaner, in the background. You do similar things, but you can remove the galaxy emission or the point source emissions much more accurately than here, but this is right? Yeah.
What is the level of these correlations?
It's here, right?
Yeah.
So here is almost unity, right? So the diagonal is unity by definition.
Yeah, of course.
But what do you mean?
You mean between very different redshift shells? It's
around here, for instance, this one here,
2.3,
0.2,
Yeah.
which is huge. It is currently physical, right?
One reason why you could see this correlation is misidentification of emission lines in the photosystem.
I see. So a galaxy that looks in reality is a different place, and then you have high correlation.
Galaxies at a given redshift can have photosynthesis at this redshift or at other discrete redshift.
Right. So they should say like regions for a given redshift, like blobs here at the given redshifts, right?
But that should give you very specific locations.
Right. So it should be like isolated blobs, for a given galaxy here, it should be maybe here, this pixel here, maybe this.
And it should be very easy to identify.
Right.
Because typically it is only H alpha, oxygen 3, and H beta.
Okay.
Sorry.
Yes.
Would this also apply even if because you used a cut on the odds,
Yes.
right? So even if there's a cut on the odds,
still there are residuals.
there must be, but
I don't know, maybe.
Yeah, I mean, these are supposed to be the best galaxies we have.
Yeah.
But yet, even they are real galaxies, most of this was caused by stars. Right? So once, if you go back here.
You can see there, sorry.
Yeah.
Go back to the, you can see there that the one between 0.35 and 0.25 is symmetric.
Yeah.
This is two lines that are being assigned the wrong redshift.
The wrong. Yeah. Okay.
Actually, everything looks very symmetric.
Yeah.
I mean, by construction, should this be symmetric? Sorry, no, it shouldn't be symmetric. So by construction, it's not symmetric. So if it's symmetric, it's because of the reasons you're telling, right? All right. So okay. So we have a cleaner survey, but not a perfect survey. This is a take home. Okay. For the ARF, it's not so easy to correct because I should correct for the redshifts themselves. I know how to correct the redshifts. So what I'm showing here, shades is pre and post. I have to change this. But now I have to do it. I just noticed. So I have to redo the plot for the paper. This is just one method computing the ARF, and this has to apply to different definitions for this new observation, these angular redshift fluctuations, right? It's kind of technical, but the fact that they are similar makes me happy. Okay, this kind of a statement. Okay, so the two things, it's typical for the ARF that the closer neighbors are anti-correlated. Okay, and they should go to 0, and this is pretty much what we are saying. And the scale of correlation should be related to the width of the shells. So this is pretty much what we are seeing. Right? So I'm pretty happy with this. Okay, the thing is, we compute CLs, right? We compute CLs. This quantity we can relatively easily compute from the map. We have the map. We can, we compute the map in this way I was showing before for the angular redshift fluctuation for the delta C's and the delta G's. And once we have the map, Yeah, we can compute the ALMs and we compute the CLs, right? This we can do relatively easy, right? But then we have to compare it to theory, right? So for that, last year, a couple of years ago, we took a standard cosmological Boltzmann code that tells you how these anisotropies evolve with redshift and so on, but not only for the CMB, for the temperature and the polarization and the lensing potential, but also for weak lensing and for ADF. So we modified it and we introduced the ARF, right? The good thing is that this code introduces or considers all relativistic conditions at the linear level, right? And it computes all cross-analysis. So this is our theoretical framework, right? You can compute theory by this modified version of CAM, okay? And then, because we're very low redshift and we are narrow shells, it simplifies a lot. And for either ADF or ARF, to the clustering of redshift fluctuations, we can break the field into two contributions. One, which is just the density contrast of matter under the this hat means under the Gaussian shell, right? It's like a projection under the Gaussian shell of the density contrast of matter or the linear peculiar velocity of galaxies, right? So for either of these two fields, we have a contribution from density and a contribution from velocity. Now, the contribution from density is modulated by the bias, and this will be the dominant term. The contribution from velocity is typically smaller, and is the one that is interesting to us, to cosmologists, because this amplitude of the peculiar velocities are triggered by gravity, and depends on cosmological parameters we're interested in, dark energy, on how much matter we have, on how this is a growth factor on how perturbations are growing with respect to time, and this is a derivative, right? This is telling you the amplitude of the velocities triggered by gravity on the largest scales, on the linear field. And this parameter we want to measure accurately in LSS, in surface, right? And here we barely measure it because we're going shallow, and the J-PLUS is shallow and not very deep and so on, but we hope to measure this more accurately with J-PLUS, and we should. So at the end, if you compute the CLs of this map, right, it's just, you can decompose the ALMs like this. So the component depending on density and the component depending on velocity. And then when you square this term and you compute the CLs, you have a term that is just depending on the density and goes with the bias square. There's a cross term between velocity and density, and it depends both on the velocity and the bias. And there is a velocity term, which is depending on this. So a priori, we fit for these two parameters, right? In reality, in order to simplify, and since this measuring this term is tough, it's very difficult because it's a small term, I'm just redefining this amplitude as the ratio of the actual amplitude of the velocity in the data over the fiducial amplitude in the fiducial cosmological model I'm assuming. I'm assuming a Planck cosmology, a Planck compliant cosmology. So I have some predictions, and then this term is just close to unity, telling me how much I'm deviating from what we expect, right? So this is constant for every redshift shell, but this depends on redshift, and this depends on the shell, the bias, okay? Okay, but this is not the whole story. Why? Because this is not a spectroscopic survey, this is a photometric or spectrophotometric survey. So actually, when you compute the predictions for the CLs, you need to introduce the DN set, which is the redshift distribution of your sources, which are Gaussians in our case, because I'm adopting Gaussians, right, throughout the. However, if we have photocy errors, then the effective DN set that we're introducing are different. For instance, for a Gaussian center here with this width, in practice, the selection is this one. The effective width of the Gaussian is the one I'm adopting, but then it's actually intrinsically being smeared by the photometric redshift error, right? So this must be another parameter I have to fit.
Okay. You assume the photometric redshift error is Gaussian.
Which is already an approximation. But the code adopts either Gaussian or Lorentzians,
okay,
right? But I'm playing Gaussian, okay? And so this is telling you how this is the ratio of the CLs. This is how the CL gets. Usually, when you have a photometric redshift error, the amplitude of the CLs get depressed, and they get depressed more for the ARF. The ARF are more sensitive to these photocy errors than the 2D cluster, right? So this is the ratio of the CLs with photometric redshift error over the CLs with no photometric redshift error, right? I have different. This is for a narrow shell of sigma 0.01 and assuming a galaxy bias of 1.2, right? And you can see that for a typical error of 0.15, it's like 0.5. The CLs drop by half of it, right? But for the same error, for the ARF, they drop by a factor of 2 or 5 more. right? So it's sorry, factor 2.5 more. So this is 2 times 10 to is 0.2. Instead of 0.5, it's 0.2, right? If you increase the redshift error to say 0.03 for a narrow shell, then the ADF dropped by 2.3, like 2/3, right? Whereas for the ADF, they go below 0.1, right? They really suppress a lot. So the ARF are more sensitive to the photometric redshift errors than the ADF. As soon as you have some errors for narrow shells, the suppression is huge. For wide shells, the suppression is not that important. Okay. So this is a new parameter we have to fit for. Okay. And now, of course, what I said before, the ARF provides linear theory predictions, where we're looking at huge scales, where on average the density contrast and the ARF are very small. We're at very low redshift. We're looking at the small scales where the density contrast is not that small. In the map, it was going up to 3. Delta E was up to 3, right? So we expect some inconsistencies between theory and the data itself, because we cannot apply. Actually, Raul Angulo and including the collaborations, we are working like crazy trying to provide predictions for the scales below 40 or 60 megaparsecs, because this is what near theory fails there, and you need to have corrections, and you need simulations, you need to understand how the variance change the distribution of matter and so on. You need to include feedback, AGN, and so on, right? So this is a hot topic. But here I'm not bothering. I know that I'm a very non-linear regime. I'm looking at small scales, but yet I fit a linear model and see what happens, right? I don't know how well you can see this, but this is the results, right? So every row here corresponds to a different redshift shell, right? This is redshift point. You cannot see a thing. I can just log out and zoom in and we do it. No, but this is redshift 0.05, 0.07, 0.09, and so on, 0.11, 0.14, 13, up to 0.25, right? And every column here are different values of sigma c. This is the narrower shells, this is middle width shells, and this is the wider shells of 0.05, okay? This is for ADF, and this is for ARF, right? I will zoom in now. You see a gray area here, so I'm neglecting, I said here that I'm neglecting the scales below 5 megaparsecs, which means, sorry, and this is multiple L, this is the L, this is the inverse number of the angle. So this corresponds to scales that are below 5 megaparsecs in projection are gray scales here. So as I'm increasing the redshift, they are moving to higher and higher L's and they get out of the plot. But I'm just fitting up to, for L maximum, below the L that corresponds to 5 megaparsecs. So I'm not fitting the gray areas because they correspond to scales smaller than 5 megaparsecs, okay? I'm not sure if it's worth zooming out and leaving the talk and getting, I could zoom into this plot, but what I'm going to stress is that typically it's a surprisingly good fit. So because I'm fitting the 3 widths at the same time, most of the weight of the fits is driven by the white shells, right? Because they have more galaxies and they have typically smaller error bars, okay? But yeah, in some cases, for the ARF, for instance, the narrow shells go nuts, go crazy. In this particular case, it's obvious, but since the data is trying to fit as well the white shells with smaller error bars, this is the fit is driven by these wider shells. Overall, yet it's a 3-parameter fit, and the chi-square is not bad at all. Typically, narrow shells are more noisy, they're noisier because you have fewer galaxies. You can see here that the error bars are very big, right? But still, they provide some information. Yeah, and that's pretty much this. And then you can see that in reality you cannot see. You may either use the ADF only to fit the model, or may use the ADF plus ARF to fit the model, right? So in blue here, and just the blue curves. Let me just, I'm gonna show you in more detail because how much time do I have?
Plenty.
Okay, so let me just do it like this. So okay, so this is the ADF plots, right? You see it here, more or less, yeah. So this is the lowest. No, I can't find my cursor here. Wait. All right, here am I?
It's better if you look on the screen.
Yeah, it's good. What happened?
Glitches.
Okay. So you see that either if I use the ADF only or the ADF plus ARF, the model is it's fairly good. At least this is for the first redshift shell. You see the redshift here is 0.05, right? Okay, I'll cheat one here. Yes, and but the two models are very close to each other, right? The fit fit is, as I said, is driven by the wider shells with 0.03 or 0.07 or 0.05, sorry. But the two fits are kind of compatible. at least for the low redshift shells. As you increase the redshift, the impact of systematics is a bit higher. Low, but yet it's decently good, right? So at redshift 0.15, yeah, the two fits, either you're using ADF or both ADF and ARF, are surprisingly good, right? Here at the small scales, you may have negative, you have to correct for short noise, which is something I don't want to get into. So, but you have larger uncertainties and you might get negative points, but that's not an issue. I mean, I understand that, but so it's fine, right? And then when you go to higher redshifts, the fits start to degrade a bit. This is for the ADF. Still, the two things, still decently good, right? Even though we know that the impact of systematics is not negligible, right? This is redshift 0.25. Same story or similar story for the ARF. For the ARF, what we find typically is that at low redshifts, where we have nonlinear velocities, for the narrowest shells, the predictions are off what we measure. However, yet the model, is driven by the fit is driven by the wider shells, and this is what and this is what weighs more, right? As you increase slightly the redshift, things tend to improve slightly, right? And then actually you're fairly good, right? And of course, as you go to very high redshift, you still have some hints here. You can see that indeed the fit driven by only ARF, which is the green, or the ADF plus ARF, they start to differ slightly, but not widely. Okay. So this is what we do. So the green is just only ARF, and they try to fit the data, the best it can, right? When you combine it with the ADF, there is some inconsistency, and then you move out of the model. Because typically, the error bars for the ADF are smaller than for the ARF when you combine both of them. Yet, I mean, I was surprised to see these fits in a positive sense. That I expected it was fits. So I'm running a Monte Carlo Markov chain for this with this set of parameters, right? I'm fitting a different value for the bias per redshift shell, the amplitude of velocity, and then I'm fitting the error, the Gaussian error for the photosets, right? And there are two approaches there. I may assume the same error at all shells, or a different error for every different redshift shell. And the results, okay, let me go back here, take off glasses, and then, okay, so the results of fitting that model on this data, well, you can see the results of the fits. So these color curves are the best fits after doing the Monte Carlo Markov chain. And this is the result, right? And so this is in this case where I'm assuming that this is the same sigma error. This is sigma error is the photo-C error, right? Assuming Gaussian errors. These are the bias.
I'm sorry.
Wow. Hello.
Alejandro?
No, I haven't seen anything. So I wanted to warn you that now we see slides, so it's okay.
Okay. So there's some delay between. Okay. So yeah, this is pretty much Alejandro, the outcome of the paper, right? So we're trying to fit the different parameters. Here is the photometric redshift error, either from ADF alone, from ARF alone, or by combining the two observables, right? This is the bias, redshift dependent bias, and this is the amplitude of the velocity with respect to the fiducial amplitude we expect for this cosmological mode, right? This is assuming the same photo-C error in all shells, or below in the bottom panel, either we may assume it depends on redshift. Okay. So what happens? Obviously, well, first of all, LeFar, when I take Antonio's photo-C PDFs, I compute what is for this sample of galaxies, what is the expected uncertainty error, sigma error for these photo-Cs, and it's 0.013, which is fairly well what the ARF are measuring, right? Also, the combination of the two is pretty much what the ARF are saying, right? The ADF go crazy, and they blame and they assign a much higher photometric redshift factor. Because there is some, first of all, the ADF, my interpretation is the ADF are more sensitive to nonlinear physics, right? They usually get contaminated by nonlinear evolution, but also there is like a degeneracy. You can assign higher photometric redshift errors, which tend to suppress the amplitude, at the expense of increasing the bias, and you obtain the same final result. So they typically, the ADF provide higher values of the bias, but also higher values of the sigmas. But at the end, they end up with similar sigmas, right? So as you see, there is an increasing trend of the bias. The ARF, which are the red squares, they kind of follow a power law. There's some shell here going to be crazy, but more or less same power law. Beyond point 18 or 20 for the ADF, they get flattened, right? This I suspect is systematics, right? But I haven't proved this. If I had to bet on something, I'd bet on ARF, right? Up to point 18 or so, they give compatible results, right? Well, not really because of this thing, right? When I'm adopting this model, where I'm assuming that the sigma c is the same for all shells. If instead I let the photometric redshift error to depend on the redshift, then I see that for the most nearby shells, the photometric redshift error estimates of the ADF and ARF are consistent, right? And again, they are oscillating. They are typically lower at low redshifts. They increase at higher redshifts, but they are not far from the 0.13 average value provided by Antonio, right? And in this case, because then interestingly is that at low redshift shells, the photo error estimates are compatible from ADF and ARF. The thing is that at high redshift shells, the ADF want very high errors, and this is true in this distribution we see in the top panel, right? But there is compatibility below redshift 0.15. Okay, and then of course, can we measure cosmology? Can we do cosmology? Not really, right? So ARF in the top panel, we see things are compatible with 0 because essentially the contribution is very small to the CLs. The contribution of the peculiar velocities with this small area and with this level of photometric redshift errors is very small, right? The funny thing is that because of systematics and nonlinearities, ADF are actually pointing to a very abnormally high value. And when you do the combined analysis, you may claim, hey, I'm detecting peculiar velocities with a photometric redshift survey like J-PLUS. And in reality, this is just driven by the systematics and nonlinearities of the ADF, right? So I think we should only look at the red curves, at the red contours here, which is we are fairly sensitive to velocities. We expected this somehow because the contribution is very small. But I think my take-home message here is that that ARF work, they do at least as good as the standard 2D clustering. I would even blame, quote that I tend to believe more this evolution, this steady monotonic evolution of the bias with respect to redshift, which is what we expect. But anyway, I never defined what the bias was, right? So the bias, we're assuming that light traces matter. We're assuming that galaxies are sampling how the matter distribution in spaces, right? So you have some regions where you have overdensities or underdensities of matter, and we believe that galaxies are fair traces of that. We believe that modulo a constant, and this constant is the bias, right? This is telling you how galaxies are tracing matter. They are either more clustered or less clustered, and this is this bias parameters, right? Anyway, I was saying that I tend to believe more this bias estimates from ARF than from ADF because of this systematics kicking in at redshift 0.2 or so. But overall, below 0.2, the two things are perfectly compatible. And that, unfortunately, with J-PLUS, it's not only the photo errors, it's just that we have very small cosmological volume. We're going up to redshift 0.2. This is a very small cosmological volume, right? If we had this level of accuracy, photo accuracy, but on wider cosmological volumes, I think we should probably detect this, right? But we're not there. So this is the same thing with the corner plots. So there is, again, ADF is blue, ARF is green. They tend to be, this is in the first model where I'm assuming that sigma c is constant, right? And it's clear for the velocity, there's some inconsistency between ADF and ARF, right? Because ADF prefer these abnormally high values for the photo errors. But if I go to the second approach where I let the sigma c error vary with the redshift, then the first 11 squares here are the photo errors, and the next 11 ones are the bias. What I want you to see is that at low redshift errors, at low redshifts, in this first 5 bins or so, there is no tension between the blue and the green, right? And then as I increase the redshift, attention starts to build up, right? But anyway, I think this is hard to see the result. I think we should better look at this plot, which is more informative, right? Yet every of these plots are going to the paper. Yeah, so that's pretty much what I wanted to say. So take home message is here is that we've done what we could do with J-PLUS. It was we didn't do any cosmology, but at least it made us develop tools for building the mask, for correcting for systematics, which is a pain. It's something critical that is impacting critically on all survey, galaxy survey. We have been testing our machinery to compute the ADF, ARF, the angular power spectrum, to implement this linear model, to obtain constraints thereof. And what we find is that the bias seems to behave in a sensible way. It increases with redshift, as one would expect, and that below 0.15 in redshift, ADF and ARF are comparable. There are evidences for systematics and mismatches at higher redshifts. And the cool thing is that I think it's the first time, and this is fairly new. I don't see of any analysis in any volumetric survey where the actual clustering analysis is providing a measurement of the photosphere. It's usually given as an input from the photosig code guys, telling you this is your photosphere error, and then they input this. Here we're inferring from the data, and we get good agreement with you guys here. Yeah, I hope to share this, having an exam tomorrow, day after tomorrow. So this is delaying me, but then next week, I really hope to share with you. Draft, it's been 3-4 years, I forgot, right? But well, it's 2 papers and tools that we're gonna be using for J-PLUS. And this is the positive outcome of all this. So that's it. Thank you, guys.
Thank you very much, Carlos. Questions?
Somehow, especially when you were showing the diagonal plots that you were showing before.
For the correlation.
This one.
Yeah.
So I was wondering how these plots, but in general, the whole work compare between J-PLUS, which is a photometric survey, and spectroscopic survey, like BOSS.
Okay.
Because I would expect
don't think-
spectroscopic surveys to be better, but the question
There
is
will be
how
a big
much.
difference because
Alright.
the off-diagonal terms here are driven by systematics, right?
Right.
So it depends how well BOSS cleans for systematics,
Okay.
which is not extremely good. We know that we cannot go to very large scales because there are star residuals, there is extinction residuals. They still provide weights, and they do a terrific job in trying to correct for them, but that correction is not perfect either, right? So before correction, they will look kind of similar. I don't think there would be a very big difference because most of these off diagonals, maybe the diagonal, which is due to cosmology, will be better defined, but then these off diagonal terms would be very similar before correction. After correction, I bet it's going to be kind of similar. But having done the test, though, that's an interesting test that you do, right? Yeah, it's an interesting test how well they corrected it. But yeah, but this is like a bottleneck. So usually these residuals impact when you have residuals at this level when you have large redshift increments. When you create large redshift increments on the sky, you have large distances. On very large distances, when you compute the number of galaxies, very large distances, it's where it's more likely that you have some residuals of the systematics because of the star density slightly changes, because of the extinction slightly changes from one observation to observations. So on these large scales, when you do cosmology with galaxy surveys on large scales, you are really limited by systematics. And there are some cosmological parameters on these large scales you can very hardly measure. And this is a serious problem. It's been a serious problem all throughout for BOSS, for EPOS. And for Euclid, we hope this is going to be better because we don't have the sky. Yet you have zodiacal light, you have extinction from the galaxy, and you have stars, right? So it remains to be seen how well we do with Euclid, right? It remains to be seen. Surely we won't be perfect, right? Yeah. And there is some cosmology that is suffering. It's a parameter which tells you how inflation, the very early epoch of before when this universe was expanding at a speed larger than the velocity of light. It's a parameter telling you how the quantum fluctuations that got stretched, whether they were Gaussian or non-Gaussian. Some inflationary models tell you there should be some level of non-Gaussianity, which is a parameter that you only measure when you actually study the clustering on these very large scales. Okay. And the measurements of this parameter have been suffering a lot. This is in the community, it's not how big or deep your survey is, it's how well you are correcting for systematics and whether you believe that correction for systematics, right? So
this is sort of an a priori knowledge.
Yes.
Okay.
Yes. So you can finish. Well, you measure this parameter from the CMB, very clean, right? And you know that this parameter is small, it's below 5, right? And if you don't apply any correction on the galaxy surface, then you measure that this parameter is 300. But you see, okay, it's obvious we have systematics. And even after correcting for systematics, we have upper limits of 50, 180, 40. Now, using the ARF are actually less sensitive to the systematics. We're writing now a paper with my postdoc there. We're claiming 40 as an upper limit, right? And yet, this is with Quaya. We're using Quaya, which is the quasar catalog from Gaia. And yet, from space, we see that at very large scales, we are limited by the extinction of the galaxy, and we have systematics as well, right? And this is limiting our ability to constrain this parameter, which is on the large scales. So this is a problem for every sample. I will have to do this.
Oscar Niños.
Yeah, it's just a comment in the discussion and why is this thing? Because at the end, yeah, with the spectroscopic survey, you have better redshift, but at the end, you are counting the number of objects. So you need to refer that spectroscopic to the parent sample. So at the end, we end with the same problem.
Yes. The spectrum make no difference. The spectrum make no difference, right? Because the spectroscopic sample is inferred from the photometric sample. And the selection is done with photometric sample.
Right. Sometimes you need, what is the weight, even in redshift? When I was working in Marseille, was like, oh, I need always the ratio between the total sample and my spectroscopic sample, even in redshift beams, which I don't know, because this is why I measure the spectroscopic redshift. So at the end, you need photometric redshifts, some quality to derive these weights. And then you have the problem with the photometric, all these photometers.
Right.
At least here, perhaps you have one step less.
Yes, one step less. Simpler this way.
Okay.
So, yeah, one question. So I understand you are using the dark area of the survey. So the dark area of the survey. Your results.
Yes. And you see
Have
the full footprint. Yes.
Yeah. Have you tried to break it in different areas to see if you are getting similar or different results? Would be that useful?
Yes and no. Right. Thing is, if I break the survey into chunks, into different parts, I lose information on the angular scales that are bigger than the chunks. In the lowels. The lowels are corresponding to the bigger angles, right? Angles that are bigger, say that my chunk is this thing, right? I just get this thing, right? So the L's, the multiples that are related to angular scales bigger than the size, I will lose information, right? I will just stop that information. But you're right. For smaller angular scales, for the CLs on high L's, on this region should be the same, this region should be compatible, and this is done sometimes to check for consistency and that you're not doing the systematics and so on.
But I mean, if you find differences,
You should worry about it.
you should worry about it, or you are understanding something you didn't understand before in terms of physical universe.
The theory, no. We know the universe must be, we know it's homogeneous, right? At least from the CMB, it's extremely homogeneous. And with the surveys, we see pretty much there's no big difference between this channel and this channel, right? And they have been tested. Tests such as computing the CLs, angular power spectrum, north and south, modulos on calibration. We might have systematically find less galaxies here than here because systematically have more extinction here than here. Once you correct for that, then you see that the angular statistical properties in the spatial or angular distribution of galaxies is the same, right? So you will find something very different from here to here, to whatever. Okay. And this happens. Like for BOSS, they had the northern chunk and the southern chunk. And actually, they don't want to do a joint analysis because this makes things up. Because the depth is different here than there. And so they cannot combine, right? So they combine after the analysis. They can combine constraints after doing the full analysis. But they run different pipelines in the north and the south, right? The same pipeline, but different. They don't just gather the whole data in the same thing because here the depth is different than here, right? And this is causes a problem. But we know it's observation because they noticed that the extinction was different on average, larger than the north, right? And this propagated through the entire analysis. But yes.
Yeah. So you apply a cut in the odds of 0.8.
Yep.
This means that in every redshift beam, you are probably selecting the most luminous galaxies. So do you think the angular distribution of these galaxies is representative for the whole distribution of the baryonic mass? The bias could be different.
Yes. I mean, let me think loud. You're saying you're selecting high-Earth galaxies, which are typically the most luminous ones. Yet we think that they're the most luminous ones, they are the most massive ones. They are typically having a higher bias. Because usually this bias increases with redshift and increases with halo mass. Okay?
Yeah, probably the most massive galaxies are more clustered.
That's right. That's why the bias increases, right? So you simply are selecting a subsample of galaxies with typically higher biases, right? That's the right? Higher luminosities, on average, corresponds to more massive halos, which are more clustered, and which correspond to higher values of bias. So, but yet the underlying assumption and what we see in numerical simulations is that even if you have fewer halos, because they are more massive and they are more scarce, they are not so abundant, they are fiducial, they are good tracers of the underlying total matter density. It's just that you have fewer and they are more strongly clustered. And this is reflected in the bias state that you have.
Do you expect substantial improvements when DR4 is released? It will be about 4,000 square degrees with more contiguous.
Maybe when we're still far away from measuring. And my hope was to measure velocity, this AV, right? And if you go to the plot, still way far, right? I don't think that by it's a kind of a pity, right? Here we have kind of a peak, still from one. Yeah, ideally I like something. I'd like to have something closer to the thing, right? And I think that maybe 5,000, 6,000. You should do it. We should. I think that's. I think it's probably it's not gonna. I'm scared. Yeah, I'd love it for this to happen, but it's not probably not. Well, but only if it fits. If we get this big shift in the slide to higher, surely everything goes. Showing that we still keep some sensitivity to the velocity. Right? That's the thing. We're limited because these velocity terms in the angular power spectrum show up only at very low multiples. But these low multiples are limited by the relatively small sky fraction. So we increase this. Then by increasing the sky fraction, we increase our sensitivity. Yeah, I'll do it. We'll have 4,000. I don't know when will be the next data release for J-PLUS, because I understand we're busy now with J-PLUS and so on. But we should try. The pipeline is ready, it's just changing the catalogs and just letting it run. So, relatively easy.
More questions? No. Thanks again, Carlos.
I have a question. Sorry. I have a comment. Can you hear me?
Yes, we can hear you.
Okay. So thank you, Carlos, for the talk, and sorry not to be there. I'm much closer. No, not in Teruel. I'm not in Teruel.
Okay. Mm-hmm.
So no, I am actually at my parents' house in Avila.
Okay.
Don't care. No sweets.
But going to Madrid soon, so even worse. Anyway, so I have a comment about something I'm not really sure I understood. You were showing a correlation between two redshifts values, and if I understood, Antonio was commenting that it could be due to misidentification of emission lines.
Yeah.
Well, I cannot help myself when I'm watching a conference to do some numbers, so I was computing, and I don't think that's the case. Sorry, I see no line that could be misidentified from redshift 0.25 to redshift 0.37, at least with J+. So it could be something else. Maybe the absorption, maybe the Balmer break. I don't know. That was.
So the way I understood Antonio's comment is that there would be a possibility for J-PLUS, that typically if you have misidentification of lines, then you would find like spots in off-diagonal, in off-diagonal pixels, right? On a given row.
Yes.
We'll find like here and there, right? Of course, you know, the redshift range here is so shallow, so narrow, that
Yeah.
I'm not surprised from what you're saying. Yeah, it's probably very unlikely to find confusing lines in such a narrow redshift range.
Yes, that could happen, but it would have to be redshift 0.05 to redshift 0.3. So the gap between the wavelength distance between the strong emission lines is bigger.
Yeah.
That was the
makes sense.
Anyway.
Makes lots of sense. So these stronger lines, which were like this O2, H alpha, which lines did you go through?
I have tested O2, H beta, O3, and H alpha, and there's no way.
Okay, good to know. Good to know, Alejandro. That may go.
Yeah.
Thank you.
Anyway, thank you.
Okay, any other question here or in the online audience? If not, thank you.
Thanks to you. Thanks to the hospitality of Cerca as well. It's always a pleasure to come back here and work, even though most of you are away. Bueno, pues nada, bueno,